So let's talk about the lab from yesterday. So you had that spring that was oscillating back and forth. So here's the deal, is that you have three types of energy involved in the system. You have UG, you have US, and you have kinetic energy, okay? So here's what you're doing, is you're just continuously changing the energy between these three forms. That's all you're doing. So if you look at, like, let's say, for example, you start at the bottom, okay? So if you start at the bottom of that oscillation, you won't have any kinetic energy because of the fact that it's changed direction and it's at the bottom, okay? So you won't have any kinetic energy. Then, as it starts to go up, okay, then you're going to increase your UG because you're lifting this thing up. Oh, okay, right? But you're decreasing your US because the spring isn't stretched as far. So when it hits up the top, that's when you've built the maximum UG that you can build, because that's as high as it's going to go. So your UGs that are maximum, your kinetic energy is back to zero, and you have a minimum amount of US. So then as it falls, it's just going to switch places. So you're going to increase kinetic energy, and then it's going to start to decrease. You're going to increase US because you're stretching the spring farther, and then you're going to decrease UG because it's falling. So all you're doing is continuously changing that form between kinetic energy, US, and UG. Okay. So what you should get then is, if you were to like look at the graph of, say, kinetic energy versus time, okay? And let's say that you were to start at like the top of the oscillation. Well, if you were to start at like the top of the oscillation, you'd have no kinetic energy, and then it would fall, and then it would hit a maximum, and then it would come back down. So your kinetic energy graph would look something like this. So if you start at like the bottom of that oscillation, it has no kinetic energy, then it's going to go up, and so this is when it's like halfway through the oscillation. And then at the top of the oscillation, that kinetic energy is going to go back to zero. So that would just, and then it would get smaller and smaller and smaller because you're always losing energy to friction. So as that spring oscillates, what's happening, and spring's pretty cool if you think about it, because the particles have like a memory. So when they get stretched, they remember to go back to where they were. But when anytime you're making atoms move past each other, that generates heat. Now, you know, you don't make this thing oscillate and then it gets so warm that if you grab it like you're going to burn your hand. You're not generating that much thermal energy, but you are generating some of it. And then it's also, as it's moving through the air, it's generating a little bit of friction because of the fact that because we have an atmosphere. So those two combine to always dissipate that energy. Okay, so make sure on your graph, okay, of force and elongation, you should have some data points like this, okay? And you're going to draw that line of best fit. It's like, what was your maximum elongation that you guys had?
0.182 meters.
0. What?
182 meters.
0.182? Okay. So here's what I'm going to look for on Kara's graph. I'm going to have her go out to 0.182 meters, and I'm going to have her draw a line straight up, and then where that, I don't want that data point necessarily, I don't want that amount of force. What I want is the value of the force that corresponds with that maximum elongation, okay? That's what I want. So if this is 0.182, I want to see Kara's line go straight up, cross this point, and then I want to see that data point written, 0.182 and however many newtons that is, okay? Now, if that happens to be the same as her point on the graph, on her data, that's fine. But if it's not, then I need to know what that is. And then she's also going to have maybe a couple of points circled and those points written down so that I can see how she calculated that slope. Okay? So what you should see, hopefully, on questions 6, 7, and 9, that all three of those answers are pretty much the same. Kara?
So, on 7,
Yeah?
you wanted us to use 1/2 kx squared, right?
Yes.
Okay.
And so like, what did you have for your slope?
My k value?
Yeah.
80.
Okay, so you have 1/2 80 newtons per meter times 0.182 meters squared.
Okay. So then on 9, is it just?
So Kara.
I mean, I got the same.
Kara. I'm going to show you exactly how to work this. Okay, when you came out here
The corner.
to 0.182,
Mhm.
and you came up here, what was the force that corresponded with across this line? On your graph, what did you have?
14.7 newton.
14 point what?
7.
Okay, 14.7. So we're going to call this 0. We're going to call the other point 14.7. So what's the average between, if I asked you to find the average between 0 and 14.7, what would you do?
Add them up and divide it by 2.
Add them up and divide it by 2. So you're going to take 0 plus 14.7 and divide that by 2. And then, so that's going to be our average force. So in other words, it's just like this average force going across like this. And then multiply that by 0.182.
Okay.
That's all you have to do. Do not make that complicated. Do not make that complicated. Okay. Anything else? We're good on the multiple choice. So let's make sure everybody's cool on that not last multiple choice question with the wheelchair. So here's the deal, right? And there's the wheelchair, boom, we're going to go up like this, right? So when I talk about this being 10 meters, this is the distance that I'm talking about. I'm not talking about it being a 10-meter long ramp, okay? It's 10 meters high, which is a pretty good jump. I mean, if you consider this ceiling to be like 2.5, okay? This person's wheelchair is going to be up there quite a ways. So, Shivani, listen to me. Power is work divided by time, okay? It's not work times time, it's work divided by time. So here's the deal. So you got a 300-watt motor, so you know this number. Now, your work is going to be the force that you have to apply, which is going to be the person's weight, times that height of 10 meters. So remember, when you have an inclined plane, you can calculate the work one of two ways. You can either take the force parallel and multiply that by the length of the ramp, or take the person's weight and multiply it by the vertical distance that it gets lifted. You don't have enough information to calculate force parallel. You don't know what this length is. You don't know what the angle is. You can't calculate force parallel if you tried. You don't have enough information. But what you can do is, because you know the total mass, the wheelchair and the person, you can calculate this value here. You know the height. You know this is 300 watts. The only thing you don't know is time. Okay? So there's that. All right. Anything else on the lab? Going once? Going twice? So, okay. So a couple of housekeeping items. So the seniors, which is everyone but you, is done, not next week, but so basically in 2 weeks y'all are done, okay? So after today, you only have one more Friday of high school, so that's kind of cool. So what's going to happen is that you're going to have one test over energy, okay? And that test over energy is going to be next Wednesday, okay? So we've got to do like center of mass stuff today, and then one big kind of summary assignment on Monday, then review on Tuesday, have the test on Wednesday, and then we need to spend some time going over some thermal stuff like thermal expansion, gas laws, buoyancy, and then you're going to have like written final, and then we'll see how we're doing on time. Then hopefully we have time to do a lab final, but we'll see how that plays out. Okay? So here's what's set in stone: is a week from, or next Wednesday, is a big energy test. Okay. So here's what we've got. So when you look at collisions, you can have two types of collisions. You can have elastic and inelastic. Okay? So if you have a perfectly elastic collision, and you would have to be told this is a perfectly elastic collision, you can serve two types of things. You can serve energy and momentum. Okay? So if you are told that it is a perfectly elastic collision, okay, and this is like an idealized world, when you have a collision, you don't lose anything. So however much energy that you have at the beginning is the same amount of energy that you have at the end. So if I drop this ball, and that was a perfectly elastic collision with the table, what that would mean is that this ball would bounce back up to the same height every time, okay? And no energy would be lost in terms of the energy of motion, like kinetic energy, potential energy, that type of thing. Now, in reality, that doesn't happen because of the fact that you hear that ball hit, okay? So we're losing some energy to sound. When we distort that ball, right, then we lose some energy there because we've got to make the atoms that make up the tennis ball expand and contract, right? So perfectly elastic collisions are this idealized perfect thing. Now, in inelastic collisions, you conserve momentum. So here's what's always going to be true, is that momentum is always conserved, okay? Because momentum is a one-trick pony. Momentum is just momentum. It's mass times velocity. That's it. The thing with energy is it's nebulous. Energy can be sound. Energy can be thermal energy. Energy can be UG. It can be us. It can have KT. It can have rotational energy. You can have all these different types of energy. Momentum is a one-trick pony. It's a cool pony. Don't get me wrong. Okay, but it's just mass times velocity. That's it. So here's the deal. You will always conserve momentum, but you will only conserve energy if you are told that it is a perfectly elastic collision. So, now I'm going to go through the beginnings of a whole bunch of weird math. Don't write this down. I'm not going to expect you to derive this equation, okay? Don't flip out. I'm not going to expect you to do this. I'm just going to show you where the idea comes from, okay? So, here's the deal. So let's say we want to conserve energy. So let's say we're going to have two collisions, right? Okay? So let's say we're going to have kinetic energy of a bullet plus the kinetic energy of the target is going to equal the new kinetic energy of the bullet plus the new kinetic energy of the target. So it starts just like momentum, but the only thing is that we're going to talk about energy. Okay? That's it. So we're going to do the energy part first. So this would be 1/2 the mass of the bullet times the velocity of the bullet squared plus 1/2 mass of the target, velocity of the target squared. This is why this is a long process, okay? And that 1/2 mass times the new velocity of the bullet squared plus 1/2 mass velocity of the target squared. Okay? So this is how this is going to start. Okay, it's this big long equation. Now, you all know how I feel about fractions. I'm going to get rid of them. So I'm going to multiply everything by 2. So that way I don't have to worry about that. So boom, all of the fractions are gone. Multiply both sides by 2. Don't have to worry about it. Now, what I want to do is I want to get all of the bullets on one side, and I want to get all of the targets on the other. Okay? So I'm just going to move this over. So I'm going to have the mass of the bullet times the velocity of the bullet squared minus the mass of the bullet times the new velocity of the bullet squared. That's going to equal the mass of the target times the new velocity of the target squared minus the mass of the target times the original velocity of the target squared. Okay? All I did was just combine the terms. Now, I want to factor out a mass to make this a little bit cleaner. So this is going to be the mass of the bullet times the velocity of the bullet squared minus the new velocity of the bullet squared. It's equal to the mass of the target times the new velocity of the target squared minus the velocity of the target squared. Okay? Cool with this. Just did a little bit of algebra, did a little bit of rearranging. Now, for now I want you to pretend that that doesn't exist. Okay? Let's go back to your math class. If I said, I want you to factor x squared minus 9, difference of 2 squares. So when you factor the difference of 2 squares, what do you get?
Equal.
What do you mean?
Like x plus 3, x minus.
Okay, x plus 3 times x minus 3, right? Difference of 2 squares, the FOIL method, x squared minus 9 plus 3x minus 3x, you get back to this, right? Digging deep into the recesses of your algebra mind, okay? But that's how you do the difference of squares. So we're going to take advantage of that, and that's what we have here, okay? We have the difference of 2 squares, just like if you had x squared minus 9, okay? It's the same idea. So this is going to be the mass of the bullet times the velocity of the bullet plus the new velocity of the bullet times the velocity of the bullet minus the new velocity of the bullet. And that's going to be the mass of the target, v prime t plus vt, v prime t minus vt. Okay, so I'm just going to stop right there for just a second. Okay, we're going to circle back to this idea. So all I did was I took the idea that energy is conserved, and I did some algebraic mojo, and I ended up down here. So everything is still equivalent. I haven't changed anything. I've just done a bunch of rearranging and some factoring. Cool with this. Like I said, don't flip out and think, oh my God, are we going to have to do this on the test? No, you won't. You're fine. Now we need to look at momentum. Okay? So momentum is actually a little bit simpler, because that's just going to be, mass of the bullet times the velocity of the bullet plus the mass of the target, the velocity of the target, mass of the bullet, new velocity of the bullet plus the mass of the target, new velocity of the target, right? This is simpler because we don't have the squares, right? So I'm going to do the same thing. I'm going to move this bullet over here, and we'll factor out the mass right away, so we're just going to save us some steps. So this is going to be the mass of the bullet times the velocity of the bullet minus the new velocity of the bullet. And that's going to be the mass of the target times the new velocity of the target minus the velocity of the target. Okay? So here's what we're going to do. Since these two things are equivalent, I'm going to take this line here, and I'm going to divide it by this line here. Okay? So imagine I'm going to take this whole thing, because they're equivalent, and I'm going to divide this by the mass of the bullet, velocity of the bullet minus the new velocity of the bullet. mass of the target times v prime of the target minus vt. Now, here's where this is going to simplify a lot. So at this point, I'm going to cancel out the mass of the bullet, and I'm going to factor out this whole thing. I'm going to lose the mass of the target, and then I'm going to lose this whole thing. So what I end up with is the velocity of the bullet plus the new velocity of the bullet, okay, is going to equal the new velocity of the target plus Vt. So here's the deal. So if it's a perfectly elastic collision, this is like a nice little check that we can have. So in other words, when I add together the velocities on one side, they have to equal the velocities on the other side. Okay, so if it's a perfectly elastic collision, this is going to help out a lot. Now, at this point, I'm not going to go through this because this math even gets weirder. Okay, so if you substitute and do some other things back in to combine some terms, and this is the heart and soul of what you're going to need. Okay, this is the heart and soul of what you're going to need. So to calculate the new velocity of the bullet, this is what you need to write down. Mass of the bullet minus the mass of the target Now, if you need this on, this equation isn't on your equation sheet because it's a real specific equation. But like on today's assignment, I've got it at the bottom of the equation sheet. If you need this equation for the test, I will give this to you on the test. Here's what you do need to understand, is that on a perfectly elastic collision, you conserve two things. You conserve momentum and energy. This is how you're going to find the new velocity of the bullet. This is how you're going to calculate the new velocity of the target. Now, think this through. If you notice with this is the mass of the bullet times the velocity of the bullet. So when you do this, when you take the mass of the bullet times the velocity of the bullet, what are you finding? Momentum. So this is twice the momentum. Okay? And then I'm going to divide it by the sum of the masses. All right? Now, here's what I want to look at. The variables here are the masses, okay? So if you look at this situation, you can have three different situations. The mass of the bullet can be greater than the mass of the target. The mass of the bullet can equal the mass of the target. The mass of the bullet can be less than the mass of the target. Okay? So those are the three things. So you can have something really big hitting something small. They can be equal, or the mass of the bullet can be less than the mass of the target. And that's typically what happens. Okay? So here's the deal. If the mass of the bullet is bigger than the mass of the target, when I subtract this, is this going to give me a positive or negative value?
Positive.
Positive, right? So if this happens, and typically we're going to define the velocity of the bullet as being a positive value just to make it simple. So if the mass of the bullet is bigger than the mass of the target, then what's going to happen is that the bullet is going to keep going in the same direction. And I'll show you this in just a second. Now, if the mass of the bullet equals the mass of the target, okay, they're the exact same size. When I subtract this, what am I going to get? 0. So if the mass of the bullet equals the mass of the target, the bullet's going to stop. Okay? Because if you think about it, that has to make sense. Oh, right. My momentum and energy have to be conserved. So in this collision, if the mass of the bullet and the target have the same mass, the bullet's going to stop, and the target's going to take off with the exact same momentum and the exact same energy that the bullet had before the collision. Okay? Now, Matt, what if the mass of the bullet is much less than the mass of the target? Then what am I going to get? The sign out of this. Positive, negative, So this would be a negative value. So what that would mean is that the bullet is going to change the direction, it's going to bounce in the opposite direction. Okay? So there's three things that can happen. The bullet can keep going in the same direction but slow down. The bullet can stop, the bullet can hit and bounce back. Okay? So let's look at each of those scenarios. Get this to spin. Okay. So, here's the deal. So we'll put a 1 kilogram mass on this one. So this is a really, really big bullet hitting a target. Now, typically what we're going to do is we're going to make this simple, and we're going to have the target be at rest. Okay? Because that way we don't have to worry about it moving. So you always assume that the target is just at rest unless you're told something differently, and I'm not going to do that. So you always assume that the target is at rest. So I've got this bullet coming in, right? Now, interesting thing happens. The bullet, when it hits, notice that it keeps going, right? The bullet keeps going in that same direction. But look very carefully about the separation. So when this hits, notice that the target is going faster than the bullet was. So the distance between these two is actually getting greater, because when this hits, this one takes off. Okay? So this one's going to slow down a little bit. It's going to lose some energy. It's going to lose some momentum. But that's going to get transferred to this. Okay? Got that idea? Now, situation number two, they're the same mass. So if they're the same mass, this one's going to hit. Now, notice that this one stopped. Okay? This one stopped, so my bullet stopped. The target is going to take off with the exact same momentum and the exact same energy that this one had. So if they're the same mass, we hit, boom, this one stops, this one takes off. Okay? Scenario number two. Now, scenario number three, you have a small bullet hitting a large target. Now, in that situation, notice that the bullet stops, ricochets, and bounces back in the opposite direction. Okay? So you hear, boink, changes direction. Because mathematically, when you take the mass of the bullet, which is small, subtract it from the big mass of the target, you get a negative number, which means this thing stops and bounces back. So here's your three scenarios. Big bullet, small target, boom, that one takes off like a shot. This one keeps going in the same direction. Same mass, boom, one stops, the other one keeps going. Scenario number three, you hit and you bounce back. Okay? Those are the three things that can happen. Now, what can't be a perfectly elastic collision is like a California problem. So if I've got this one at rest, okay, and they move in, hold on, okay. Now, in this situation, they move off together. When you have a California problem where they hit and move off together, that cannot be a perfectly elastic collision. Mainly because the math just fails, okay? Because these two are going to be moving off at the same velocity, right? So you can't calculate separate velocities because they're moving off together. So when you have a California problem, you still conserve momentum. Okay, the momentum is still conserved. This has the same momentum as the one did before. But you don't conserve energy, because what happens is that in that collision, you lose a certain percentage of that energy in making them stick together. Okay? So, California problems can't be perfectly elastic, but you're still going to conserve momentum. So you always conserve momentum, but you don't always conserve mechanical energy. Okay? Got that? Okay. Now, how it works. So let's say okay? So here's the deal. So I've got a big bullet moving at 4 meters per second, and it's going to collide with a 1 kilogram target that's at rest. So this is my bullet, and this is my target, right? So this is going to move in. I'm going to tell you it's a perfectly elastic collision, okay? So here's the first thing I want to find, is that I want to find the new velocity of the bullet, okay? So I'm going to come up here, it's a simple calculation. I'm going to go, okay, that's going to be 3 kilograms minus 1 kilogram times 4 meters per second, and then I'm going to divide that by the total sum, which is going to be 4 kilograms. So I'm going to divide that by 4 kilograms, okay? So basically the 4s are going to cancel out. I take 3 minus 1, I get 2 meters per second. Okay? So the bullet was coming in at 4 meters per second, and it's going to slow down to 2 meters per second. Okay? So it's lost some momentum and it's lost some energy. Now, where is that momentum and energy going to go? It's going to go to the target. It's going to go to that other one that was at rest, right? So now I can go, okay, now I want to calculate the new velocity of the target. So the new velocity of the target is going to be 2 times the mass, which is 3 kilograms, times 4 meters per second, divided by 4 kilograms. Okay, so the 4 is going to cancel out. I get 6 meters per second. Okay, now, at this point, we can do a little check. Okay, so if this is a perfectly elastic collision, here's what we're going to do. We're going to look up here and go, okay, is this statement true? So the original velocity of the bullet was 4 meters per second. It slowed down to 2 meters per second. So that's 4 plus 2, that gets me 6. Okay, so this part, so we're good so far. The original velocity of the target was 0, okay, so we don't have to worry about that. And then we said the final velocity of the target was 6 meters per second. So far, we're good. These two velocities here of the bullet add up to the final velocity of the target. Okay, so we got 6, hey, life is good. Okay, now, let's see if we actually conserved energy. So we had a 3 kilogram mass moving at 4 meters per second. So Shivani, how can I calculate the original kinetic energy of the bullet?
1/2 mass times velocity squared.
Beautiful. So I'm going to take 1/2 times 3 kilograms times 4 meters per second squared. So that gets me 16,824 joules. Okay? So that's the original kinetic energy of the system of 24 joules. Now, afterwards, I'm going to take the 3 kilograms, and it's going to be moving at 2 meters per second. And then the 1 kilogram is moving at 6 meters per second. So I'm going to take 1/2 of 3 kilograms times 2 meters per second squared. So that gets me 6 joules. And then I take 1/2 times 1 kilogram times 6 meters per second squared. So that gets me 18. 18. Because 36 is 1/2 of 18. So I get 6 plus 18, I get 24 joules. So my kinetic energy before equals my kinetic energy after. Okay? So I've conserved energy. Now, if I want to conserve momentum, and that's going to be easier, oh, that's just 3 times 4, okay, that's 12 Newton seconds. And then this is 3 kilograms moving at 2 meters per second, so that's 6 Newton seconds. And then I have 6 meters per second times 1 kilogram. Voila, I've conserved momentum and I've conserved energy. So it's a perfectly elastic collision. Now, in terms of how this actually manifests itself, the only time in nature we actually see this happening is when you have collisions of like nuclei of atoms, okay? Because otherwise, like with carts or anything, there's always going to be some friction. You're always going to lose some energy to sound and stuff like that. But here's the deal. So in reality, it's rare that you actually have perfectly elastic collision. It's a good model, okay? But in reality, it's not going to happen. It's just like a cool freshman. Possible, realistically not going to happen, okay? And I'm sure you all were exceptions to that rule, because I'm sure you all were cool freshmen.
Not Matthew.
I bet Matt was kind of cool as a freshman.
Hey, I told you the second
Okay.
half of me.
So we have one concept left for today, and that's center of mass. Okay? So here's how you kind of demonstrate center of mass. So I've got these boards, okay? I'm going to lay them out like this, okay? So what I'm going to do is I'm going to push this one further out. So if I push that out, eventually what's going to happen? It'll fall. So right now the center of mass is back here on the table, right? So as I push that out a little bit farther, what I'm doing is I'm shifting the center of mass further and further and further out, right? Okay, a little farther, a little farther. Ooh, we can just kind of balance it. Okay. So that's right there. That's pretty balanced right there. So if I go farther out, and if I let go of it, it's going to fall. So here's what you have. All this is showing you is that the center of mass is dependent upon two things. It depends upon where the mass is and what the value of that mass is. Because if I take, I don't know, this beaker and put it back here, now what's going to happen to the point where that goes before it tips over?
It's going to go further.
Yeah, it'll go further out because I've shifted that center of mass more towards this side. Okay? So now with this one, I can't even make it go far enough without the center of mass of that one falling off the edge of the earth. Okay. So center of mass is somewhat similar to torque, but not really. So to find the center of mass, you take the mass of A times the position of A plus the mass of B times the position of B, and you keep going on and on and on. And then you divide that by the sum of the masses. So what you can do, one way to find the center of mass is to use your fingers, okay? So if I take this and hold this up like this, and I begin to slide my fingers together, my fingers are going to meet at the center of mass, which is at that 50 centimeter mark, okay, because I have an even distribution. Now, even if I start with one finger really close and this one out here, it's still going to meet in the middle. Now, but what if I take ET and put ET, whoop, come back, don't phone home yet. So what if I put ET on there? Now what's going to happen?
Center mass is gotta be closer to ET.
He's going to fall, okay? So now, where's the center of mass going to be?
Closer to
Closer to ET, right? So now, notice that this one, we don't meet in the middle because the center of mass is shifted to the left. I'm still going to meet where I can balance it, and you can do this with aircraft carriers, airplanes, cars, whatever it is. If you have like a big enough lift, if you can put it up there, you can find the center of mass, that one point where it's going to balance.
I can't lift an aircraft.
So,
with my fingers.
here's how this would play out.
Yes.
So let's say that you have a board, okay, like that, and I'm going to put a 1 kilogram mass,
You think they could lift?
0.2 meters from the edge, and then another 0.2 meters,
You're probably right.
I'm going to put a half a kilogram mass, and then another 0.2 meters over, I'm going to put a big massive 5 kilogram mass. Okay, so in other words, imagine this, I've got this board. I'm going to put, so I'm going to measure in 0.2, I'm going to put the 1 kilogram mass, put a half a kilogram mass, and then I'm going to put a big 5 kilogram mass. So what I want to figure out is that where is this thing going to balance? Okay, that's what I'm going to try and find. Where is this thing going to balance? So here's the deal. The formula is pretty simple, but here's the only thing that you have to watch. You have to start on one end. And these distances are from the pivot point. They aren't how far they are from the previous one. Okay? So like this first one, I'm going to have 1 kilogram times 0.2 meters plus a half a kilogram. Now, with this one, I've got to use a distance of 0.4 because I'm measuring it from this end. So don't use 0.2, I've got to use 0.4. So that's going to be 0.4 kilograms. And then I'm going to have 0.6 meters times 5 kilograms. Okay? So, before we do any math, okay, Karen, do you think the center of mass is going to be underneath the 1 kilogram, underneath the 0.5, or closer to the 5 kilogram?
Closer to the 5.
Yeah, that's where I've got my most mass. So what I'm trying to figure out is that point where this thing will balance out. Now, if you do all this math to save us some time, you get 0.523 meters. So what this means is if you measure from this end out to 0.523, which would be about right here, this is where this thing would balance. So that's where you could put that fulcrum, and this is where this thing is going to balance. So this is important. Obviously, like if you're flying an airplane, okay, all right, so let's say you've got like this little Cessna, right? And especially if it has like a triangle landing gear, like this, well, you don't want the center mass of this airplane to be back here. Because if you do, it's going to go doink, okay? That's going to be bad, right? So you want to make sure that you know where that center of mass is located. The same thing is true like if you look at the Apollo missions, okay? When the Apollo missions were returning back to the Earth, where their center of mass is located within that ship determines its trajectory. So you always had to be very cognizant of where that center of mass was, okay? If you're on a ship, okay, You don't want that center of mass to go off to one side, because then it's going to start to shift to that one side. So actually, center of mass is very important in terms of like transportation and keeping things stable. Okay. One last equation, and then we're done. And it's pretty simple. So up to this point, how did you all calculate change in momentum?
V minus VR.
Mass times
Change minus VR.
change in velocity, right? Which is mass times V minus V naught, which is equal to force times time. Now, let me get a balloon.
Oh, he's getting the balloon out.
Huh?
He's getting the balloon out.
What are we gonna name it?
Jeffrey.
No.
I'm gonna let go. I'm not gonna keep him blown
Okay.
up.
Now he looks like a brat.
He looks like a blowy.
Blowy.
Okay. So now I let go of this balloon. What's it gonna do?
Fly away.
He's going.
Will it accelerate?
And
Yes, right? Will a force act on the balloon? Yes.
Has to.
Is the mass of the balloon gonna change? Yes. Why is the mass of the balloon gonna change?
because the air is gonna go there.
Because the air is going to be going out of it, right? Oh, that was a good one. Okay. So that basically acted as a rocket ship. So when you have rockets, okay,
That was a good throw, Matthew.
it wasn't bad. So if did anybody see yesterday where SpaceX finally stuck the landing on the? It was pretty cool. Anyway, so they launched the ship, and then it had famously crashed like 4 or 5 times, like completely blown up, and they finally stuck the landing yesterday. So they launched it, and then the rocket came back down and landed back on the landing pad, which is actually more difficult than getting it. To get it to go up is simple. Oh, okay. But then to get it to come back down and land, to reuse that rocket, that's actually some seriously good engineering to make that happen.
The rocket goes up. Who cares where they come?
Huh?
That's not my department.
What'd you say?
I said the rockets go up. Who cares where they come down?
Unless you're China, because they've got a massive rocket that's right now out of control, and they don't know where it's going to come back into on a reentry path. So hopefully it goes in somewhere in the oceans, but they really don't know. Kind of embarrassing. Oh, we launched the rocket, and then the main stage started to orbit. It went up too high, and it got caught in the orbit. But what's happening now is that it's starting to hit our atmosphere, so it's starting to slow down as it gets into a thicker part of the atmosphere. That creates drag, that slows it down even more, and that creates more and more friction. So this thing's going to be this big, massive fireball when it re-enters the Earth's atmosphere. And hopefully it doesn't hit like Mays High School, hit by falling China rocket.
I mean.
No school.
Okay. All right.
You're right. They'll have to go-
So here's the deal with rockets. How rockets work is that all we're going to do is we're going to change the location of the delta. So rockets work by changing mass, and this is the velocity of the escaping gas. And it still equals force times time. So the only thing we did is that we changed the location of the delta. So you all are used to having a constant mass multiplied by a changing velocity. Rocket engines work by expelling gas at a high rate, like the balloon, and this is the rate of change of mass. So rockets keep a constant velocity, and you have a changing mass. Most of the time, up to this point, you all have kept a constant mass, and you've changed the velocity. Okay, so that's been the difference. So with this one, and it still equals force times time, it's still kilograms meters per second, so it's still Newton seconds. It's the exact same units. So clearly, if you want to generate a lot of force over here, you have a rapid change of mass. So the more fuel that rocket can consume per unit of time, and the faster that gas is being expelled out, the greater the force that you're going to have. So basically, if you move this time function over here, so what you want to focus on if you're an engineer is that how do we get the most fuel consumed per unit of time and have it kicked out at the highest velocity. So if you're a rocket engineer, you look at change in mass per unit of time. If you're a safety engineer for a car company, you have that time over here, so you have a constant mass, and you want to increase the time for that change in momentum to happen to decrease the force. So if you're a safety engineer, you want to decrease the force by increasing the time. If you're a rocket scientist, you want a big force, so you want a big change in mass per unit of time multiplied by a big velocity. Okay. Oh, dear, 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 dear. Okay, so on this assignment, so number one is just old school, okay? It's old school momentum. You got Timmy, he's sitting in a boat, okay? Like this. You have his mass, and he's going to throw out a rock. So here's Timmy holding a rock. So he's going to throw the rock in one direction. So what does the boat and Timmy have to do? They have to go in the opposite direction. Okay? So number one is just old school momentum. Momentum forward equals the momentum afterwards. Now, on number two, this is a rocket problem. You're going to use this idea right here, that force equals change in mass per unit of time times the velocity. So I've given you the escaping velocity, 4.00 times 10 to the fourth. It's expelled at 1,500 kilograms per second. So I've given you this number. You just want to calculate the force. And again, what unit should it work out to be in force? Newtons. Okay. Now, when you talk about number four, okay? So when you look at number four, we're going to be talking about rotational kinetic energy. Now, rotational kinetic energy is 1/2 I omega squared. So number four, I'm trying to get you ready for the final. Okay, so number four is going to go old school. So kinetic energy equals 1/2 I omega squared. So if I take this wheel, right, and I make it spin, it has a certain amount of kinetic energy. But it's rotational kinetic energy because it's only spinning. So clearly, the faster something spins, the more kinetic energy that you're going to have. So if it's going slowly, it doesn't have much rotational kinetic energy. If I double the speed, I quadruple my rotational kinetic energy because it's omega squared. Now, also, remember torque equals two things. What does torque equal?
Force and distance.
Force times radius. It also equals I alpha, right? I fish. So, you have a solid cylinder. You've got to go back and look at how you calculate the moment of inertia of a solid cylinder. Okay? You can look on your equation sheet, it's on the back side. So, you want to find the rotational kinetic energy, the work that was done. Now, what's the initial, look at this wheel, what's my initial rotational kinetic energy? 0. Did I do work on it just then? Did I increase the rotational kinetic energy? So what do you think the relationship is between the work and the change in the rotational kinetic energy? They're the same. So just like work equals a change in translational kinetic energy, work equals a change in rotational kinetic energy. It's the exact same concept. Okay? It's the exact same idea. And then it asks for how much power is required. Oh, power is work divided by time. So you find your change in your rotational kinetic energy, which is equal to your work, and then you use that divided by time to get your power. Okay? On number 5, I tell you that it's a perfectly elastic collision. So down here below, I've got the equations for perfectly elastic collisions. Okay? Don't have to look them up. They're right here. Okay? Here they are. But then on number 7, you're going to have a box moving, and then it's going to hit box at rest, and then they're going to move off together. So here's the difference between 5 and 7. 5 is a perfectly elastic collision. 7, they're going to hit and they're going to move off together. Okay, that's going to be the difference. Now, when you get to number 10, here's the Earth, here's the Moon, not to scale. You want to find the center mass of the Earth-Moon system. Now, if you're clever, which you all are, you're going to let the distance of the Earth be 0. Okay? Just start right there. It's just like a balance. I'm going to let the Earth be here, and I'm going to define this position as 0. Out here is going to be the Moon. And you know that distance. So, I would let the position of the Earth be 0, and then the position of the Moon is that 3.84 times 10 to the 8th meters. Okay, so you got this times 10 to the 8th meters. Okay, now to give you some perspective, and I saw a cool graphic on this. You can actually fit all of the planets, if you stack them side by side, Jupiter, Saturn, you can stack all of the planets in between the distance between the Earth and the Moon. So we have enough room to stack all of the planets in between. So anyway, so use this as the distance to the Moon, and then you have the mass of the Moon, and then divide that by the total mass. When you do number 11, I don't care which end you start with, okay? But I tell you to give the location in reference to the 1 kilogram mass. So again, what I would do is I would define the position of that 1 kilogram mass as being 0, and then I'd move out from there. Okay, I'm done. Have a good weekend. You have one big energy assignment on Monday, review on Tuesday, test on Wednesday. So that's the story, kids.